Okay, so good morning. Let me thank the organizers for the invitation to this beautiful place. So the title has changed a little bit, although the themes are the same. I'm going to talk about two signatures of topological matter beyond topological insulators into 3D systems. The first is how glide operation protects novel states, and I'll show some new results based on the nonsymmorphic metal, potassium, mercury, antimony. And the second part will be sort of a review of the chiral anomaly findings. I'll rapidly review the experiments and then update you on tests of why this interpretation of the chiral anomaly is valid. And I acknowledge the supporters of our research, especially the Moore Foundation. So the one recurring theme in topological matter is the symmetry protection of states. It's not the only theme, but it seems to be the one that you can follow continuously. And Murakami in yesterday's talk, it's a very nice talk yesterday, talked about how codimension, right? When the codimension equals the dimension of K-space, that automatically guarantees protection. The second part of that is that when that doesn't happen and you have to bring in additional symmetries, he briefly alluded to that. This is what makes it experimentally more interesting, right? So here we are talking about symmetry protection of a node that doesn't rely on codimension being equal to the real dimension, but you have to add in further symmetries. And this is actually very familiar in topological insulators. So let me just quickly remind you what the Chemists Theorem is, probably totally unnecessary for this crowd. Right? So if you have two states that you hypothesize to be degenerate, you can write them this way, right? They are both eigenvalues, eigenstates with the same eigenenergies. Then under time reversal, this will happen, right? Because theta, the time reversal operator acting twice, will give you -1. Okay, I'm talking about large spin orbit systems. But then because it's anti-unitary, the time reversal of the matrix element becomes the flip of the matrix element, right? And then using the first equation, you see that this quantity, the matrix element, is the negative of itself and therefore must vanish. So this is very well known in atomic physics and molecular physics, but we would like to, okay, so the punchline is that these two have to be orthogonal and therefore they must be distinct, even though the starting hypothesis didn't make that assumption. So this is the famous Chemists degeneracy. Now to apply to K-space, we need the little group because we need a symmetry, and usually the operation will kick the K wave vector to someplace else. We got to bring it back, right? And so this is called the little group. Let me remind you. So given a space group, the little group is the subset of the space group that doesn't change the K vector. So it brings it back to itself. Either one of the elements by itself or multiplied by time reversal. Okay, so then now we can apply Chemists Theorem to protect the state. Now in the familiar example, so this was the grandfather of all examples in topological matter, Kane and his co-workers showed that time reversal is enough. Provided you have the wave vector pinned to the what's called the time reversal invariant momentum. This is simply a long way to say that it's got to be pinned to the corner or at the gamma point. So actually the math seems more obscure. Pictorially, it's very clear what's going on. If you happen to have your Dirac node here, under time reversal it goes to there. But then these 2 points are linked by a Bragg wave vector. So you're back to the starting point. And that alone is enough to guarantee that the node, the Dirac node is protected here and in the center, right? Now, this is nice. It started the whole field, but it's also a severe restriction because now you cannot place your Dirac node anywhere except at these corners. Space groups actually are mostly nonsymmorphic. So this is just a big word meaning that they have glide and screw operations. So starting fairly recently, 2 years ago, suddenly many groups, theoretical groups, realized that this is a very rich area because most space groups are nonsymmorphic. So let me quickly remind you what glide operation is. In fact, this is the material we're talking about, a cartoon of it. If you reflect about this vertical plane, then it's not a symmetry operation, right? So blue goes to gray. That's represented here. However, if you now translate by half the lattice spacing, you're back to the original structure. So glide means reflect about a particular mirror plane and then translate by half or fraction of a primitive lattice vector. So it's usually written in this Seitz formulation, a reflection about the plane denoted by x, followed by or preceded by a translation of a fraction of a lattice spacing. And let me remind you, mirror reflection is given by in the usual representation by an inversion followed by a pi rotation. Now, why go to the trouble of having glide operation? So you remember I told you that the preceding argument would need to have the protected node sitting at the corner, but if you have glide operation symmetry, you can actually protect it over an extended region. And this, again, pictorially, let us skip the math, right? If you start from anywhere here, time reversal brings you down to here, right? So you cannot get back, right? If you use the Bragg vector, you would get back to here. But now under reflection, you come to k prime, which is again identical to k, right? So under the product time reversal and gx being the glide operation, you bring yourself back to k modulo Bragg vector. Now, why is this interesting? Well, when you do it twice, going through the math, you see that you pick up a -1. So it's just like time reversal in the TI, but now for a rather interesting situation, this works no matter where you are. Okay, you recall that I said that in TI you're pinned to here, but now you're protected along this whole surface, right? And this results in the sticking of bands all along here. And this is actually known to Herring. Herring was the first guy, Cornelius Herring, found this effect in 1937, and he coined the term sticking of bands. So this is one advantage, that you can protect the node over a huge region. The second advantage was realized just very recently, and that is the Mobius band topology, right? So initially I talked about this part, but now along this side of the surface of Brillouin zone, you don't need time reversal, right? Because if you start off here, reflection will bring you to here, and then this is identical to that point. So the little group, so to speak, is G itself, but now it comes with an interesting eigenvalue, and the eigenvalue comes about because of this 1/2 translation. The eigenvalue is plus or minus I times this interesting phase factor from the block translation. If you stare at this, you see that you get 2 eigenvalues. So these two are actually 2 distinct branches with a period of 4 pi, right? So if you move along this direction, you actually are not protected, but your eigenvalues pick up 2 values, and they twist by 2 pi. They exchange if you go up by 2 pi. Right? So this reminds you of Mobius topology. If you start from one edge and you go around by 2 pi, you end up at the bottom edge. And this is exactly what's happening. And the term Mobius band was coined by some of the theory papers that I referred to. So we have two things working here. If you move along UZ, that's the upper branch, you have the herring sticking, right, that I mentioned, which is represented by these two, these double lines here and here. But then when you hit this point, they have to exchange because, right, you have to switch from M plus to M minus, and therefore these two states that were initially degenerate have to switch. And that gives rise to this hourglass fermion that Brnovik and his co-workers discovered. So this is the material I'm going to be talking about, but our finding actually goes, I think, beyond the theory. It's very puzzling, so I'm going to share this with you in the following slides. Okay, so this is the famous paper that I was referring to. That's potassium, mercury, antimony. And it's comprised of a graphene-like two-dimensional layer, more like boron nitride, actually. So it's mercury, and then X can be antimony or arsenic. And then it's staggered from one layer to the next with potassium sitting in the middle. And as advertised, you see that if you go along one edge of the surface Brillouin zone, the bands stick together, but then when they turn the corner, then they have to exchange, and that gives rise to the hourglass fermion. So there are two basically findings here. One is that if you have a crystal, let's say like this, and you point your magnetic field perpendicular to the planes, you will see quantum spin Hall states that surround the side walls. Right? These are actually, yeah, they are actually the states that stick together, because UZ is along the Z direction. But then if you look at dispersion along the Z axis, you may pick up the hourglass fermions. We haven't been able to do that. We have just been focusing with the field pointing in the Z direction. Okay, so Kava's group grew crystals of this material, and so here are some of the sort of starting points. The mercury has this very irritating tendency to exude to the surface, so you have to be aware of that, right? So and furthermore, because the potassium tends to make it very air sensitive, everything has to be done in the glove box. But my students managed to do that from experience with sodium-3 bismuth. And this is the typical resistivity. So this is one which is nominally undoped, but there will be some residual carriers coming from the loss of mercury. So you always have a small number of N-type carriers sitting at the bottom of the conduction band. Then we managed to actually dope it by putting bismuth in, and that reduced the residual carriers. So the resistivity is higher, but we still haven't been able to drop it into the gap, right? So that takes a lot more work. But anyway, it's already interesting. So we have, instead of an insulator as predicted in these band structure calculations, you actually have a semi-metal or a metal with a very low carrier density, and you can actually tune the carrier density by adding bismuth. If you point the field in the Z direction, you see very large quantum oscillations, and you can reach the lowest Landau level right here in 10 Tesla. So with bismuth doping, we can even drop it down to 3 Tesla. But anyway, things start to become interesting when you enter the lowest Landau level. But meanwhile, if you look at the levels here, they enable you to estimate the Fermi surface caliper. And by tilting the field, you find that it fits a quasi-two-dimensional behavior. So the Fermi surface in K-space looks like a cigar that points along the Z-axis. Yeah?
Can you point where you think you are in the filling?
Yeah, so it's just the bottom of the conduction band. So all these states are in the gap. Unfortunately, I didn't show it here, but the dispersion has a conduction band and a valence band. So we are at the bottom of the conduction band. But it will turn out that because the bands are inverted, the bottom of the conduction band has a very strong hole character. And I'll come to that at the end. Are there other questions? So nothing I've shown here is worth talking about, right? It's just a boring semi-metal with very large quantum oscillations. So the first hint that something was interesting came because my student plotted out the Hall angle. And he noticed that the Hall angle displays a very sharp anomaly exactly when you enter the lowest Landau level. Right? And this is actually bewildering because nothing should happen in a conventional semi-metal, and we've been studying that for quite a while now. The Hall angle is always a straight line. It's linear. But anyway, so this is very odd, very difficult to understand. Moreover, it's very temperature dependent when it gets into the lowest Landau level, whereas it isn't in the before that. Right? And this is to show that, well, okay, I've shown this graph already. This is the temperature dependence. The quantum oscillations are huge, and then they enter the lowest Landau level. That's when the Hall angle starts to show an interesting deviation. So it's very frustrating because we couldn't get a high enough field to follow it. But by going to the magnet lab, we could track it down. So initially, we went to the DC field of 35 Tesla. And we found that the Hall angle not only comes down, it comes down and almost reaches 0. But it's very temperature dependent. Now, if you want to think about it in terms of conventional physics, all you have is are carriers at the bottom, n-type carriers at the bottom conduction band. And in the high field regime, they're basically executing tight cyclotron orbits. They should not be displaying a temperature dependence at all, much less a Hall angle that goes to 0. So by going to even higher fields and pulsed fields, we now see that the Hall angle not only plummets at very low temperatures, it actually goes to 0, dead 0, and then it stays there. So it's 0 all the way to as high a field as we can push it to. So this is the sample. Right? So it depends on the doping, right? So if the doping is too high, it's harder to reach this interesting regime, right? So this is the sample where we initially could reach it. Now you see the full anomaly appear. The longitudinal resistivity increases by a factor of roughly 80 or so, but it tends to saturate. Nothing interesting there. The Hall resistivity is interesting, right? So initially, at high temperature, it's nominally linear, maybe with a little bit curvature. But then as you drop below 30 Kelvin, it starts to flatten out, and then it just drops, it plunges exponentially, and then again bottoms out at 0 and sticks to 0, right? So this is peculiar because semi-classical dynamics would predict that these orbits will continue, and then they will scatter from impurities. Every scattering event pushes them sideways, and that generates a Hall effect. And a Hall effect shouldn't be very different from the semi-classical regime. So something here is happening, and it looks like if you sit at a high field and go down in temperature, it really approaches 0 exponentially. All right, I'll show you this in different ways. So here's a blow-up of the data I just showed you. Hall angle, it's negative. It comes down linearly, it doesn't change with temperature, reaches a sharp peak, and then starts going back to 0. And if you go to low temperatures, it dead ends at 0 by 40 Tesla, and it sticks to 0. But if you warm it up, it's thermally activated. It turns out it's thermally activated. The Hall conductivity shows the same thing, and again, it dead ends here. But it's exponentially activated. So later on, I'll show you a fit where we can extract the temperature dependence, and this is consistent with a gap, a very large gap of about 12 millivolts at 60 Tesla. So this is strange, because the semi-metal in 3D, the Landau spectrum is gapless. It's got to be gapless, right? But here we are seeing manifestly a gap, and the gap is actually protecting an interesting 0 Hall state. Now, what convinced us that this is actually a property of the lowest Landau level and not a field-induced effect is that we went to the low-dope materials where, as I said, doping with bismuth, you can drop the residual carrier density. Now we get into the lowest Landau level at 3 Tesla, and the sample is more disordered because of the bismuth doping, so you don't see quantum oscillations that you can resolve. But anyway, the same thing happens, right? It's nominally linear, and then it turns around and drops 0. But now it reaches 0 at 8 Tesla, within the field range that we can reach in our lab without going to the national lab. And again, the same activated behavior is apparent. So here we can again fit it to get a gap, somewhat smaller because the field is smaller. The gap obviously changes with magnetic field. It's roughly linear. Okay, so since it's activated, the first thing you think about is that, well, conductivity is additive, right? The Hall conductivity is additive. So you can write it in the form of 2 terms. And the lower one, the ground state, has 0 Hall conductivity. And the other one is thermally activated. So that's the fit, right? No theory involved, just by arguing about the boundary conditions. And allowing the gap to be field dependent, the adjustable, you can fit it to all the curves, and the fits are very good. So that there's no walking in and out as the curve follows the data. It actually captures the curvature very well, and that's how we determine the gap, right? So this is, and it works for both the bismuth dope samples as well as the nominally pure sample. So the message that comes through is that there is a gap, and it's not expected in 3D Landau states, but it's protecting the 0 Hall states. So it's sort of reminiscent of the 2D quantum Hall effect, except the Hall step is at 0. But it's a 3D system. So this is, we're still stretching, puzzle over this. The longitudinal conductivity, meanwhile, remains finite. It's coming down very rapidly, but it's, you can see that at the lowest temperature, it tends towards saturation at a value that if you took in how many 2-dimensional layers you have, will correspond to a fraction of a quantum of conductance. So this seems to indicate that, well, the Hall conductivity is going to 0, a gap is protecting the state, but the longitudinal conductance may be carried by these surface modes, quantum spin Hall states. But anyway, that's what we think at the moment. Now, for the, all right, so we know a lot about the band structure because of ab initio calculations. And so Bernovik's postdoc and student has actually applied a magnetic field to the calculations. And this is what the Landau levels look like. So here I'm plotting in this hybrid plot energy in the vertical axis and kx and ky, right? So the lowest Landau level has a weak dispersion, but along the x direction, when it hits the surface, it comes down. So even though this is in the conduction band, it remembers that it came from the whole band because of band inversion. So the lowest Landau level actually disperses down when you hit the surface. And if your Fermi energy is on the blue rectangle, that is where we think it is, then you see that this surface mode will intersect the chemical potential to give you these quantum spin Hall states. But calculations based on this scenario will not produce a gap. And we've been trying very hard, and I think we need some new ideas. So this is a more realistic plot of the band structure. So you notice that the lowest Landau level, so that's where we are, right? So the chemical potential is somewhere here. The lowest Landau level, when it hits the surface, it will come down, thereby giving you a surface mode that's Hall-like, and the higher levels will disperse upwards. And the uppermost band in the Hall will actually have a electron-like dispersion. So that gives you 4 quantum spin Hall states, 2 right moving and 2 left moving. and you intersect 3 of them or 4 of them depending on your filling. But as I said, there's no apparent gap in the spectrum anywhere. Okay, second part of my talk is how am I doing?
Half. 20, 25 minutes.
Oh, okay, good. Okay, good. All right, let me now switch gears. Yeah. Sure. Which part? Here? No, this puzzled me a lot too. This is kx, but in the Landau gauge, right? So kx is related to the by the magnetic length to x. It's basically the center of the orbit. Are there other questions before I leave this topic?
There seems to be a small gap at the age.
Small gap where?
0.35.
Sorry? Here?
The age gap, yeah.
Here?
Yeah.
No, this is a resolution problem.
Oh, I see.
These are real calculations. Yeah, I forgot to mention one thing. So I mentioned the sticking of bands. You see it right here. So when you are at kz at pi, so this would be at the top of the B1 zone, right? And that's where the glide symmetry protects your surface modes all along the z plane, and the manifestation is right here. So instead of a gap forming, you have you have a protected crossing. It doesn't hybridize. So that's the Herring sticking right there. So here we are at kz equals 0, which is right here. These are not protected, so they split. Yeah.
Just out of curiosity, this is centrosymmetric, right? And so I was wondering, just could you speculate on what would happen if you were breaking inversion symmetry?
No, I don't know if they're centrosymmetric. Right? If you reflect about, yeah, I guess it is. Yeah. Yeah. But what's the question?
So like if it broke inversion symmetry, do you know roughly what might happen?
I don't know how you would break it.
Strain, like if it is undergoing a diffusionless phase transition at low temperature.
I don't know.
Or if you did it on purpose.
You can break inversion symmetry. Unless it changed the crystal structure.
Yeah.
Yeah.
That's what I meant.
Yeah. Okay. All right. Let's go to my second topic. So it's more or less the same crew with a few additions and subtractions. So I'm going to review the chiral anomaly, and then I will update you on recent tests. We came up with one, which I call the squeeze test, to talk about it. And then I'll talk about some new results, rather similar experimentally to the results that Ando showed yesterday, but from a totally different theoretical interpretation. All right, so as all of you know, if you have a Dirac semi-metal, like sodium-3 bismuth, the marching instructions to experimentalists is as follows, right? You apply a magnetic field, and this will cause each Dirac pocket to split into 2 Weil nodes, and each Weil node is a monopole source or sink of Berry curvature, and the appearance of the Berry curvature, it was cancelled in zero field, but then it appears. This appearance of this dipole of the Berry curvature field has a profound effect on transport. Then if you keep pushing on it, when you quantize the Landau levels, and this is where things get interesting, the chief character of the Weil node, from transport point of view, is that the lowest Landau level is chiral. Right? That's the peculiar feature about Weil pockets. So one is right moving and one is left moving. And then the theory is that if you now apply an electric field parallel to your magnetic field, you will transfer electrons from the left mover to the right mover. And so this sounds semi-classical, but now you're going from an electron that has chirality 1 to -1. And this creates what's called an axial current that is difficult to scatter, right? Because the the axial, the chiral symmetry is partially conserved, and that the impurities don't know how to handle it, basically. And so you see a long-lived axial current. So what's the chiral anomaly? So an anomaly roughly is whenever you have a symmetry that is preserved at the classical level, right, by Noether's theorem, right? You write down a Lagrangian, and Noether's theorem tells you that, okay, you have a classical symmetry, but when you introduce quantum effects, that symmetry is broken. That's an anomaly. And it occurs all over field theory. Now you have gravity anomaly, what have you. But the chiral anomaly was the first to be discovered. That's why it's the most famous one. In our context, it again represents the left mover transferring to the right mover in the presence of an electric field. But now if you have a system like a Weil system, you have a solid state realization of what's called the Schwinger model from the 60s. And Schwinger proposed that, wow, it would be wonderful if our universe would comprise of a sea of right moving and left moving massless fermions. But now we have it. We have it in these crystals, right? It's deeply related, as I mentioned, to the Adler-Bell-Jaquif triangle anomaly. And this solved a huge puzzle in field theory, because in the 60s, when people look at pion decay, the neutral pion decaying into 2 photons was very short-lived by a factor of 300 million. That's an astonishing number compared to the charged pions. And this ultimately was traced by these folks to the existence of the chiral anomaly. Now, having this current changes not only the longitudinal MR, which I'll discuss first, but also the thermal power, and then I'll talk about a Hall effect. It basically changes everything in the electron response to an electric field. And it was observed in sodium-3 bismuth, then in the half-Heusler gadolinium platinum bismuth, and also in the zirconium pentatelluride. So let me just show you some old data. Sodium-3 bismuth is actually comprised of only 2 Dirac nodes along the z-axis. And in a magnetic field, as I mentioned, each of them splits into 2 Weil nodes. So you have 4 altogether. Right? The resistivity in zero field is non-metallic. It goes up and then saturates. The Hall effect changes sign, but that's a minor point. But the surprise is that now when you point your electric field parallel to the magnetic field, you see this giant decrease in the resistance. And this is not allowed by semi-classical physics, but that alone doesn't prove it. You have to do a battery of tests, some of which I will talk about. Then a year later, my group found that in the half-Heusler, working with Kava, that the same thing happened. And here it's a little bit more complicated. This is actually, the band structure is quadratically touching protected point at gamma. But in the magnetic field, the Zeeman energy shifts the 2 quadratic bands, and they intersect to form Dirac nodes, which are wild because the magnetic field is present. And again, you see the same magnetoresistance curve, and there's a very strong family resemblance between the 2 profiles. All right, so let me briefly mention one test. So there was an initial worry, concern that, well, maybe your sample was very disordered, and you can have current paths that wind back and forth, giving you some strange magnetoresistance. So my student Hirschberger made 10 contacts and measured every pair of every nearest neighbor pair. And so there are 8 curves here, and they all overlap. So this is what convinced me that the current's uniform. The mobility is actually very low. The mobility is about 1,500. So there are no huge cyclotron bending effects. But anyway, this is uniform except at very high fields where the Hall effect tends to kick in. So this is one test that we published a few years ago. Now, but then there's this persistent worry, right, especially in the community, and I'll show you some data for reasons for that worry, that you could have something called current jetting. Now, what current jetting is, well, let me first point out the simulation. So you can solve the current path distribution for a low mobility sample. The current, I'm plotting here the potential, the electrostatic, the driving potential, and it's more or less uniform going down the sample. But when you have current jetting, you see a very non-uniform current distribution. At your point of injection, if you use a point contact, the current splays out, and then there's a very deep sink at the other contact. So you should worry, right, when you have this situation. So what is that all about, right? So if you inject your current in here in a field that is parallel to the current, right? So the forward path, the longitudinal path, has the conductivity doesn't change, but the transverse directions will be reduced like 1 over b squared, right? So electrons, the charges will preferentially move in this direction, and this leads to a bunching of the current, right? A squeezing. So a schematic, if you take a cut here, you should see that for a low mobility sample, the effect is very minimal, but for a high mobility sample, it will all bunch up, right? But the areas are the same because of current conservation. So the test is very simple. If you put your contacts on the side, you will measure a decreasing voltage, which will mimic the chiral anomaly. Why? Because the current is pulling away from the sides, and therefore the voltage drop will decrease, right? However, if you put contacts along the spine, right, along here, then the voltage drop will increase because now the current density is higher, right? So by comparing these two, you can basically test for this current jetting. Now, here's the reason why people who have been doing this for 30, 40 years will be concerned. If you take pure bismuth and you point the field parallel to the current, you will see a result that imitates the chiral anomaly, right? In zero field, look at the 2 Kelvin curve. It's finite, but then it drops like a rock and then bottoms out, right? So how do we know this isn't happening here? Well, now if you put your contacts along the spine, you see that the voltage actually goes up, right? So this is simply the squeezing of the current density. So if you measure along the spine, the increasing current density will force the potential to go up. So if you see this, there's a reason to be worried. However, the Half-Heusler passes the test. So we see that the current along the edge drops, as I mentioned, but then along the spine it drops as well. So it's happening uniformly all over the sample. It has nothing to do with current jetting. So that's what we came up with as a test. Unfortunately, the wild semi-metals, tantalum arsenide and sodium phosphide, fail. When you put your contacts along the spine, the voltage goes up, the potential drop goes up. So in my mind now, even though these are undoubtedly wild semi-metals, it's very hard to see the chiral anomaly because you have 24 wild nodes, and they are all at different chemical potentials. So this is a big challenge, actually. It's an unsolved problem. Yeah.
So whether the left and the right panel are on the same sample or not?
No, this is the same sample, of course, yeah.
But the resistance seems to be quite different because the values are
Well, that's because which one are you talking about? This one here?
yeah. One is like 10 times higher resistance than the other. The right panel is...
Well, this is resistance, so it depends on the spacing of the contact.
Between the contact are quite different.
Yeah. Also, you are, yeah. So, it's different when you inject current at the point.
If you convert it to resistivity, whether...
No, you can't because, you are basically measuring a non-standard geometry. It's like a Fender-Paul geometry. Yeah.
How many wild nodes do you How many Y nodes is half
Here we have 2 in the half Heusler. In sodium 3 bismuth, we have 4. Yeah. So the last one is a new signature of the chiral anomaly that was introduced by Anton Burkhoff. So when you have the chiral anomaly present, you have, right, you remember there were right movers and left movers, and there is a chemical potential that basically describes your carrier density, the ordinary carrier density, but there's a chiral chemical potential, and that is measuring the difference between the 2 nodes. So they are coupled by this what's called the chiral magnetoelectric effect. So, in the beginning, many people, especially coming from field theory, thought that this will lead to a new era in electronics. You point your magnetic field in a chiral material, and there will appear a current parallel to the magnetic field, even without any electric field applied. So then condensed matter types really pointed out to them that this would violate the 3rd law of thermodynamics, right? So, but nonetheless, it's a real effect there, provided you have a finite chiral chemical potential. So Burkhoff has derived the equations and showed that these 2 are coupled. That's the diffusion equation, except the chiral charge density, which is the difference of the 2 of the right mover and left mover, has a finite lifetime tau. But tau is very long because, as I mentioned, it's difficult to scatter from one chiral mode to the other. These 2 can be used to solve for the distribution of the chiral chemical potential, and the net result, let me just give you his final result, is an equation that, as Ando pointed out, is well known in ferromagnets, that if you put your magnetic field in the plane and you rotate, change the angle, you would pick up the first equation, which is called the angular magnetoresistance, and then more importantly, you will see a pseudo Hall effect. This is not a real Hall effect. A pseudo Hall effect that varies like sine 2 theta. And this has been very well studied in the ferromagnet, but in the Dirac semi-metal, there's no magnetization. Okay, thanks. So we have carried out the tests in sodium 3 bismuth. And you see evidence for this cosine squared term. Sorry, this is very recent data. But more importantly, the Hall effect. So the Hall effect does have this sine 2 theta term, which is very similar to the results that Yoichi reported. But here the interpretation is quite different. It's basically evidence for the existence of this chiral magnetoelectric effect, which in turn implies a transverse voltage that has this peculiar planar Hall effect variation. Okay, I think that's everything. Let me just summarize. So I talked about a interesting zero Hall state that appears to be related to glide protection, but in a way that, the experiment is actually delivering more puzzles than the starting theory. We see a zero Hall effect. The state is protected by a gap, a very large gap. That's why we can see it. And but nonetheless, the longitudinal conductance is finite. It's about a fraction of a conductance mode. And then I reviewed the chiral anomaly and talked about 2 tests. One is the squeeze test, and the other one is the new signature in the Hall anomaly. Thank you for your attention.